Okay, today we are going to be solving linear systems by graphing. We're going to learn basically three methods for solving a linear system. So solving this linear system, we're going to use three methods for solving them. There are three main methods. Each of them have their place depending on the type of system, how the system is written. They all are useful. Some are easier than others depending on the system. But we're going to learn those three methods. So our objective today is going to be able to write a linear system and then solve it by graphing. Okay, so first we have to know what is a linear system. So a system of equations, hence that word equations, is made up of two or more equations having the same variables. So far we've basically been dealing with like one equation in X and Y. So one, two variable equation. So now we're going to be looking at multiple equations that all work together to create what we call a system. Okay, for example, X times Y equals 8, and X plus Y equals 6. Okay. So a system of equations, so there's my two equations. So a solution, for next we're talking about a solution of the system of equations, is any ordered pair that satisfies, important word here, all the equations in the system. So we're still going to have a solution that's an ordered pair, like an X comma Y, but it needs to satisfy all of them. Okay, so if we look at this previous one, solutions that satisfy this guy, okay, if we create an XY table, would be like 0 and 6. When I add those, I get 6. 1 and 5. When I add those, I get 6. 2 and 4, so forth and so on. Like I could keep going for forever. There's an infinite number of solutions. There's an infinite number of numbers that I can add because again, we could have negative, like -1 and 7, -2 and 8. 8, -2. Could go the other way around. Okay, so there's an infinite number of solutions that here, when I add the two numbers, I get 6. But what I'm looking for is also numbers that, again, a same xy over here that I multiply to get 8. So a solution to this entire system would be an ordered pair that works in both of them. Well, 0, 6 works in this one, but 0 times 6 is not 8. 1 times 5 is not 8. 2 times 4 is. So the ordered pair 2, 4 would be a solution set for both of them. So 2, 4 is a solution to this system because it makes both of them true. Since 2 times 4 is 8 and 2 plus 4 is 6. Okay, so it has to work in both equations. So we're going to find those solutions by graphing because, again, a graph is just the set of all solutions. So when I graph this, I'm getting the set of all solutions. So first, let's go ahead. So we're going to graph this system. So here's a lot of times what a system looks like. A lot of times we put curly brackets in front of them. Oftentimes when I write them down on my paper, I write them instead of on top of each other. I write them next to each other like this, because that way I can write stuff below them and it not interfere. So I know anything I write, and I kind of sometimes I'll even do like this. So a line between. So anything I write over here pertains to this equation. Anything I write over here pertains to this one. So now I can label. So I need to graph these. So this one has a slope of 1, so 1 over 1, and this one has a y-intercept of 3. So I'm going to graph these. So let's come over here to my graph, and we're going to graph them. Okay, so I want a y-intercept of 3, 1, 2, 3, slope of 1, up 1 over 1, up 1 over 1. Okay, so we go ahead and we want to put our line through there all the way across. Oh, that's not going to work. Let's undo. Let's bring my ruler out to make sure I get my line. You want to be very careful when graphing these. Use a ruler. Whoop. Okay, So there's my first graph. So that's the equation of y equals x plus 3. So I'm going to label it. Okay. Next graph. So we have y equals 2x plus 2. So here my slope is 2, which is 2 over 1. Here's my y-intercept of 2. So we want to come over here and graph a y-intercept of 2, 1, 2, a slope of 2, up 2 over 1, up 2 over 1, up 2 over 1. Okay, so looks like that guy right there. So let's put my ruler on there, and again, all the way through the graph. Okay, I think we're kind of done with my ruler there. Okay, so this is y equals 2x plus 2. Okay, so which points represent solutions of y equals x plus 3? Well, that's what a graph is. A graph is all the solutions, meaning this point, let's grab my pointer. This point right here is a solution. The point -4, -1 is a solution. This point right here is a solution. This point right here is a solution. This point right here is a solution. Any point on this line will work in this equation. So which points represent solutions? Basically any point on the line. Y equals x plus 3. So any points on that line. So like I can just name some points. So the point 0 up 3 worked. -2, 1, right there. -2, 1. -4, -1 works. Any points, and if I go and I plug those into here, they work. If y is -1, x is -4, yep, -4 plus 3 is -1. If I try -2 plus 3, does that equal 1? Yes, it does. So any of these points, so this point and this point and this point and any point on that line is a solution. So which points for part B, which points represent solutions to that? Well, any point on that line. Any point on that line. Any point on that red line. So for example, the point 0, this point 0, 2. The point -1, 0. The point -2, -2. The point, again, I could list points for forever. Could list them forever. List them forever. There's an infinite number of points. Again, because these lines go on forever in both directions. They go forever in both directions. I could list points forever. So I'm looking for which of those points, which point works for this blue and also this red. So if we look at the graph, I'm looking for which point is on the blue line and also on the red line. Well, it would be this one right there. That point right there, which looks over 1, up 1, 2, 3, 4. The point 1. Oh, that's hard to see. Point 1, there we go. 0.14. The 0.14. Because what? It's on both lines. So how can you check that solution? Put it in both equations. Put it in. So here's my two equations. Y equals x plus 3 and y equals 2x plus 2. Replace my x's with 1s, my y with 4, and make sure it works. Does 4 equal 1 plus 3? Yes, check. I think it does. Does 4 equal 2 times 1 plus 2? 2 plus 2? Yes, I think it does. So the 0.14, and what I love about these problems is you can check your work to make sure that the point does in fact work. Whatever point you get, put it in both equations, but you have to check it in both. You have to check it in both. We're primarily going to stick with 2 equations, but you could have 3 equations, 4 equations. There's systems with 5 equations, and you have to check that point in all of them. Okay, now not all systems have solutions. Okay, not all systems have solutions. So we can classify our system based on the number and type of solutions. So we classify our system based on the number and type of solutions. Okay, because sometimes you can have more than one solution. The one we're dealing with now, there's either one or infinitely many, so we're going to classify based on the number and type. So we could classify a system as independent or dependent. The difference between these two, an independent system has exactly one solution. Like this one we did up here. There was only one number that would work in both. Whereas a dependent system has an infinite number of solutions, meaning there's an infinite number of solutions that will work. Okay, and so we're going to kind of look at what that means. How does something have an infinite number of solutions? If they are in fact the same equation. For example, sometimes it'll be written like you'll have one that will be like x plus y equals 6. And then you might have another one that's like 2x plus 2y equals 12. Okay, if I take the second equation and divide everything by 2, it actually gets me this one. So this would be a dependent system because the two lines are going to be the exact same. If I graph this and graph this, they're going to be the exact same line. So any point that works on this one will also work on this one. So there's an infinite number of solutions. So an independent system has only one, whereas a dependent solution has like an infinite number. Okay. We can also classify a system as consistent or inconsistent. A consistent system has at least one solution. So over here, both independent and dependent, both of these are consistent solutions. So if it's independent, it's consistent. If it's dependent, it's consistent because it has at least one solution. So the consistent would be both independent and dependent fall under this. Independent, that's not how you spell. I'm just going to shorten that. Independent, dependent. Both fall under that consistent category because they have a solution. Okay, which you could also have an inconsistent, which an inconsistent system has no solution. There is no ordered pair ever that will make both equations true at the same time. There's no solution. And that is possible. A no solution one would be one like this one. There is no point on this red line that is also on this blue line. There's no point. Every ordered pair over here, every single point on this line, none of those points will be on this line also. So that graph 3 is what we call that one is an inconsistent system. This one right here, that's what inconsistent systems look like. If we're dealing with just straight lines, they'll be parallel. Parallel lines are inconsistent. They have no solution. So for us to solve it, we would say no solution. It's inconsistent. Okay. So which graph shows one solution? Well, this one. This is the one that we did. There's only that one solution right there. This one right there. So graph 1. Which graph shows infinitely many? Well, it's not graph 1 because we decided that one only has one solution. This one, if you notice the line is purple, because this is actually an overlap of the red and the blue line, and red and blue make purple. I think it's kind of fun how they did that. So graph 2 has infinitely many solutions. Basically, the two lines ended up being right on top of each other. So any point on this line would be a solution. So there would be an infinite number of points. So there's an infinite number of solutions. Which graph shows no solution? Well, we just said that was graph 3. Graph 3 is inconsistent. So classify the system represented by each graph based on the number of solutions. So here graph 1 has exactly one solution, so it'd be independent. This one's independent, which means it's consistent. Okay, so we would say both. It's independent, it's a consistent, it has at least one solution, so it's independent, and I forgot the N, inconsistent. Consistent, there we go. Whereas graph 2 here is dependent because it has an infinitely number of solutions, but it also is consistent because it does have a solution. Consist. Oh, sometimes you guys, my spelling. Consistent. There we go. It's dependent and consistent, whereas this last one is inconsistent. Oh my gosh, inconsistent. Okay, so that last one is inconsistent. So we wouldn't say independent or dependent. It is not independent. It doesn't have exactly one solution. It's not dependent. It doesn't have an infinite number of solutions. It's inconsistent. Okay, now let's do some problem solving. Okay, so now we're going to deal with a word problem. Okay, now we can solve equations that have two solutions. So here we have circular and rectangular tables are set up for a banquet. There are 9 tables set up with 80 chairs. So we have 9 total tables, 80 total chairs. Each circular table has 8 chairs. So a circle table has 8 in it, and each rectangular table has 10. How many tables of each type have been set up? Okay, so we have 9 total tables. So our goal is to find out how many tables of each type have been set up. So I'm going to say X is the number of circular ones. So the number of circle tables will be X, and Y is the number of rectangle tables. Okay, so X is the number of circle tables. Y is the number of rectangle tables. So I'm going to kind of do a bit of a verbal model. So I know if I take the number of circle tables plus the number of rectangle tables, I should get how many tables total? 9, because we know there are 9 total tables. So the number of circle tables plus the number of rectangle tables will be 9. Okay. So the number of chairs at circle tables plus the number of chairs at rectangle tables has to equal 80. Because again, we have 80 total chairs. Okay, so now let's go ahead. So do you see how this is a two equation problem? So we decided that X is the number of circle tables. So that would be the number of circle tables would be X plus the number of rectangle tables, Y, has to equal 9. X plus Y has to equal 9. Okay, so next we need the number of chairs at the circle tables. Well, there's going to be 8 chairs per table. So there's going to be 8 per table here. Rectangle, there's going to be 10 per table. But we decided that X is the number of circle tables. So if I say 8 per table, that would be 8 times X, 8 times the number of circle tables. Whereas rectangle would be 10 times the number of rectangle tables. If I add those, I should get 80. So there I have my 2 equations, one there and one there. So now I'm looking for an X and a Y that will work in both of these equations. I'm going to switch colors. So I need to graph them. That's our only method right now. We're only going to be dealing with positive tables, so I'm going to deal with this just in my first quadrant. And I don't want to lose track of what X and Y represent, so I'm going to say X over here is the number of circle tables. I'm going to label. Y over here is the number of rectangle tables, because that's what we said they were. Okay, so I need to graph these. So I need to graph X plus Y equals 9. Lots of different ways to do it. I'm going to write it. I want to rewrite it as Y equals MX plus B. So I'm going to subtract the X from both sides. Negative X plus 9. So y-intercept of 9. So here's my y-intercept. My slope would be negative 1 over 1. y-intercept of 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Down 1 over 1, down 1 over 1. I'm just going to keep continuing this across. Grab my ruler and let's sketch that. So this is giving me, I want you to line up right. That's pretty good. Okay, the number of tables. So like what this is telling me is that if I have no circular, I would have 9 rectangle. I could have 1 and 8. I could have 2 and 7. I could have 3 and so forth, 3 and 6, so forth and so on. Okay, so that's just if we're talking about the number of tables. Okay, so now we need to look at the chairs. 8x plus 10y equals 80. So I'm going to go ahead, I'm going to solve this for y. I'm going to subtract 8x from both sides. So 10y equals negative 8x plus 80. Oh. And then we have to divide, this one we have to divide both sides by the 10. Okay, so I'd have negative 8 over 10 x plus 80 over 10 is 8. Now, negative 8 over 10 simplifies. They both divide by 2, negative 4 over 5. So there's my slope. Negative 4 over 5, and my y-intercept is 8. So let's come and graph this guy. Y-intercept of 8, well, that's 9, so here's 8. Down 4. 1, 2, 3, 4 over 1, 2, 3, 4, 5. Oh, looky there, I hit a point that's on the blue line. Four over 5, so there's my line there. Let's grab my ruler and graph that red one. Okay, we're looking for a point that's on both the blue and the red. I think we found it right there. Over 1, 2, 3, 4, 5, up 1, 2, 3, 4. The point 5, 4. Again, 5 is the number of circular tables. So if I want 9 tables, which again, if you notice, this is 9 tables, 5 and 4 is 9. I would need 5 circular. So 5, because x is the number of circle tables, 5 circle tables, and then 4 rectangle. Okay, and if we put them back, oh, that did a weird thing by my ruler. Rectangle. Oh, go away, ruler. Okay, so now if I put these back in the equation, it does work for 5 plus 4, that is 9. And then 8 times 5 plus 10 times 4 is 80. There's actually an equal number of people. There's 40 people on the round and 40 people on the, so 8 times 5 is 40, 10 times 4 is 40. So 40 and 40 is 80. So it does work. How many tables of each type have been set up? That many. 5 circle and 4 rectangle to seat 80 people.